Cape Town in South Africa. The story goes, a traveler comes and there's a watchmaker in town, and all his clocks and watches all show the same time. So he clearly invests in keeping them. And so the traveler asks, so how do you know what time it is? It's before the internet, by a couple of 100 years maybe. And he says, so it's easy. Up on the hill, there's a fort, and every day at noon they shoot a cannon, and then I just set my clocks to that. And then the traveler comes up to the fort and asks, so how do you know that it's noon? Well, see, I have these binoculars, and in town there's this watchmaker, and I just look at the clock in his window, and when it's 12 o'clock, I fire the cannon. So anyway, that passed the time. That was a joke. But it was funny that when I mentioned that to my friend last week, we met up in Denmark. He said, "Oh, that's totally it. It's called Signal Hill, and it's in Cape Town. It really exists." Anyway, and the cannon is 200 years old or something.
Still accurate.
Still accurate. Yes. Yeah. So we are now at 11:40, according even to the watchmaker in town. So looks like I'm about to fire the cannon. Again, welcome back. I'm Mads Torgersen, or Mads Torgersen, or any Norwegians in here? Can you say it properly for me? There you go. Yes. I'm not Norwegian. I married into this name, and she's not Norwegian either, but her great-grandfather was, so that's where it comes from. So if you were here before, like the last time I gave a talk in here, which I do every second time slot, I give a talk here. That's a deal. I talked about functional stuff in C# over the years. Now we're going to talk about the C# that's about to come out in 6 months' time, 5 months' time, C# 11, which you can kind of guess why it's called that. And when we get to C# 12, we fire the cannon. We're now shipping C# every year, and we decided that this is all driven with .NET. They decided every year now we're modern, kind of. So a yearly cadence for major versions seems about right. And we're going to turn the crank, use new numbers for every one of those. Every other one of them is long-term support and all that. And we were like, okay, I guess C# has to do the same thing. So that we can keep that, there's different version numbers. So there's going to be .NET 7 and C# 11, but at least the delta is now constant. You can always just add 4 to the .NET number and you get the C# number. We're not all that messy business from back when they sometimes lined up and sometimes went out of whack. And it's over. And we also stopped saying .0 because there was only one time in the 7s that we ventured into, in recent memory, that we ventured into something other than 0. So now we just say C# 11. Anyway, but with this frequent cadence, more and more what happens is that we don't drop a whole feature set into one language version, but we kind of trickle it out over a few language versions. This first one, though, is like a full-fledged language feature being dropped in all at once. So you see something up here that's super simple. It's a little function that takes an array of ints and adds them up and returns the result. Okay, couldn't be simpler. Still, though, up until now, this numeric algorithm with a plus in it and a 0 and so on, there has been no way to actually abstract over numeric algorithms and say, no good way anyway, to say, well, as long as it has a plus and an additive identity and whatnot, run this algorithm. That's always been a bit of a pain point in C# and many other languages. Essentially, we can only abstract over instance members, like with interfaces, for instance. And operators are not instance members, so too bad. Up until now, so we'll do magic. I'll say, let's make this generic. Take a t instead. Return a t. Have a t here as well. Let's have it. It's tea time. Clearly that doesn't work. Okay, it wasn't that easy. But You know, normally when you want to do something meaningful with your type parameters, you use constraints to constrain T to something that offers those meaningful things. So where T something or other, and I kind of want to just say I number. If it's a number, and I have to pass T back in, we can get back to that. And you know what? It kind of sort of works. Like, what you're seeing all of a sudden is that the plus actually doesn't have a red squiggle anymore, which we all know means it works. So somehow, this interface guarantees the presence of a plus operator. That's kind of cool. Okay, it doesn't have 0, but because 0 really is an int, right? But it has additive identity. It also has 0, actually. As a static member on the type parameter, like, who'd ever seen that before, in C# at least? So all of a sudden, this interface is bringing in static members, a static property, 0, and a static operator, plus. In other words, interfaces as contracts can now specify static members. That's kind of cool, right? And you know, numbers isn't the only scenario that you can imagine for that, but it's certainly a big one, right? It's because this whole operator thing has just essentially meant you can't do like any advanced math algorithms in C# in any nice way. Like, people have tried, and it gets kind of ugly. But this is good. This is strongly typed, and but how does it work? You know, and clearly it's just it's same old type inference here. There's an array of ints. We infer int. Int probably seemingly then satisfies the constraint, so it implements I number of itself, I number of int. But what is it that you sign up for when you implement that? So let's go and have a look. Here's I number. It's a big type. You know, it's a big, for an interface in particular, it's very, very big. It's like, I can do all the number, you know. If the built-in number types in C# can do it, then this interface has it. Okay, so that's a tall order to live up to. And not only does it have like a bunch of members on it, but it also has a bunch of other interfaces that it implements that each, you know, brings in more members. So it's a gigantic interface. But it means that once you do satisfy that, then you know, sky's the limit. You can do all the number, and if that's your constraint, then your generic numeric algorithms can do everything that you can do with operators and so on in C#, with number types in C#. That's pretty great. And now let's look at these members. You can see they say static abstract. You know, it's pretty obvious right there. They're static and they're abstract. They're like a contract. They're not implemented. And they're static, so they're not about instance members. They're about static members. And the way you implement one is to have a static member declaration. That would be an implicit implementation like you can do with instance members, just static. So implement this interface yourself, put your own operator implementations on it. That's fine. You can also explicitly implement if you don't want them to be surfaced on the implementing type, just like other things. The only difference is that they're static. In terms of declaration, anyway. We can get back to a little what that means in other ways. So, but you notice that there are all these, there's this long, very, very, very long, at least it's alphabetical. Like, we have very sort of orderly, neat people on the BCL team, I think, that put these things in alphabetical order. Or maybe it's actually just Visual Studio that does that sorting when it shows from metadata. I don't know, but so you saw I addition operators there. You know, there wasn't actually an addition operator down here, but that's because it's being brought in from a much simpler interface that we can go and have a look at. That really just is, I have a plus operator. And that now you realize why there are so many interfaces, because there's an interface for each one of these. And then that lets you sort of be fine-grained about your constraints. If you're writing a generic numeric algorithm that just needs plus and 0, well, you can just bring in 2. You wouldn't have to do I number like I did. You could just bring in I addition operators and I additive identity. And then you have the things you need. So that way, because not all, when you think about this, we're offering this set of interfaces in the core libraries so that all our numeric types can implement them. But everyone else can implement them too. And if you're building types that use numerics, they don't necessarily have all the bells and whistles of a full I number, right? So you want to be able to say, for instance, if you're building a matrix implementation, you want to be able to multiply matrices. Great. So you'll implement, you know, I multiplication operator and I addition operator, but there are a bunch of things that won't make sense on a matrix. And also, in order to implement those, you can make your matrix itself generic and just say, you know, where T, some other numeric operators that are the ones that you need in order to implement the matrix level operators. So you get this fine-grained control of like just requiring what you need and using what you have. So that's why the interfaces are designed like that. But this is what an abstract operator looks like. It's actually not very surprising when it comes down to it. So when you want to use these members, though, that is where things get interesting. So back to our program, I am using the members, the static abstract members of the interface, not directly on the interface, right? Because the thing about it, like when you have an instance member, like I have something of type object, and I can call toString on it, and underneath there's an actual object that might be a derived class. It might not be instantiated from object itself. It might be string or int or whatever, and it knows its own virtual implementation because there's an object there to hold on to, like, what am I actually going to do when he says that? But for static members, it's different. There's no instance. That's the whole point, right? So we can't just walk up. We can't just have a variable that's typed I number of T and then go up and call a static abstract member on it, because where would it find the implementation? It doesn't know which implementation of the interface. There's no instance to ask. So that is where this becomes quite different in how it works. The way that we get sort of an instance, the way we get a representation of the concrete type that we want to get the implementation for is with generics. So by taking a T and constraining it to I number of T, I am saying, there's a type, I'm calling it T, and it does implement this interface, and it does have concrete implementations. Like, if you try to pass a type parameter that doesn't, we're just like, nah, sorry, can't do that. It has to have concrete implementations. And that's how we get the concrete implementations, through the type parameter, which means that you can only access these static members on a generic type, or through a generic type, through a type parameter. You can't do it directly. I mean, you can walk up to the concrete objects and call the plus operator there, but you're not calling the interface member then. You're just calling the static member like always. If you want to access the interface member, you have to do it on a type parameter constrained by the interface. That is how you get at this functionality. So it's very closely tied with generics. Question?
Does this imply that, for example, if you call this add all with a float and a long, then the compiler will generate two different implementations of this method?
Does that imply that if you call this method once with with double and once with float, the compiler will generate two versions? So the answer to that is the same as it is for generics today, which is that the compiler, the C# compiler, generates just one version, which is generic to IL. And then the runtime, typically if you're running on a JIT runtime, which most of us are still, the runtime will generate, if it sees value types, it will generate specialized versions for those value types and a shared one for reference types. So that happens to be the implementation detail behind it. So actually, yeah, we should. I mean, I didn't even show you that. You know how I can make it. I can put a float in or a double in there, and now all the other ints convert to double, and the type inference now says that it's an array of doubles, and everything still compiles. And if you don't believe me, we can actually even run it. It's always a little scary. I'm not a fan of running code, but occasionally you got to do it. There you go. I'm sure you all can verify that this is the right result by careful middle school math. So, so that's sort of like, that's the core of it. You put abstract static members on your interfaces, you constrain type parameters to those interfaces. Now you can use the static members, including operators, on things that are typed T, or around, on type T. Now you might be wondering, why is it? What is it with this type argument on the interface itself? What does it need that for? Like, why do you need to have a type argument in order to have a plus operator? Well, again, let's go have a look. The reason is that, let's say we didn't, actually it takes three. The plus interface actually takes three, right? One for the left operand, one for the right, and one for the result. So it's parameterized over that. But why does it have one for itself, so to speak? The reason is that we don't want the results to be just interfaces, right? We don't want to just say, well, it takes two I numbers or two I addition operators things and returns an I addition operator, because then when you get the result, you've lost the fact that you knew very well what type it was, and now it's been elided. You want to use generics to pass through the strong types that you're operating on, so you don't lose type strength, if you will. So therefore, even this one has three, but if you look at I number, which I just went away from, but we can go back to, it only has the one, and that is the T self. So and if you look at all the implementations here, T self is there all over the place, because it's the thing that describes the actual type that will eventually implement this interface, right? The int, the matrix of something, the this and that. It's a representation of that type inside of the interface itself. So therefore, it needs to be passed in when you implement the interface. Say, hey, I'm implementing you, and this is me. And now you can refer to me with this type parameter inside of your implementations, inside of your signatures. That's why you see T-self and input and on output here all over the place. That is why the plus in our program actually produces a T as the output as well that can be added to the T here that can then be returned as a T to the caller. That's how the type strength gets in there. Yes? Is this backwards compatible with all the runtimes? No, with older runtimes, not at all. So you're bringing up a super interesting aspect of this, which is that up until, while we were still doing .NET Framework, Windows only, the runtime was something we couldn't touch because it was distributed as part of Windows. We couldn't know or influence what runtimes were there on people's machines. And so that turned out to be a big impediment, because that meant we couldn't rely on the presence of new runtime features in our language features. So we just didn't make new ones. And then when we moved over to core, we said, well, A, we don't care about new language versions being runnable on old runtimes. And B, we can now change the runtimes so that, or add new features to them, so that things can be implemented properly in the runtime. Like all the generics in C# are in the runtime. And if we did this one outside of the runtime, it would be different and weird, and it would be a very bad, there would be an impedance mismatch. So we kind of have to do it to do this feature. And we are fine with just saying that, well, if you use this feature and you're targeting an older runtime, which is going to give you a compiler error, all the new runtime features have feature flags in the BCL that the compiler is looking for, saying, does this runtime support static abstracts? And if that feature flag isn't there, it's going to say, well, sorry, you're targeting a runtime that's too old, this feature's not going to work. So that's the new compatibility story. That's the price that people will have to pay for getting actual runtime features, is that if they don't have them, they don't have them. In a way, it's kind of, it sounds kind of all right when you say it like that. yeah, that's how that works. There's one more thing I want to. You get the idea. If any more questions? I'm happy to take them. At least one or two more. Yes.
Is there any constraints or checks for like addition operator and addition identity to make sure that actually works as it's supposed to?
Like between them?
Yeah, like with addition, you want an addition identity to be able to like add identity to a number to get the same number, for example.
Yeah, I mean the language doesn't try to impose a numeric semantics in any way. Beyond, I mean, it does a little bit today by saying, well, if you have a plus operator, it has to like some of the types have to be the enclosing type, and some of them have to be the same or whatnot. They're like there's small restrictions on operators that have always been in the language, but beyond that, we don't say. We don't try to ensure that you do proper math with your math operators. We never did, and in a sense, just because you're implementing an interface now, we are not trying to be more harsh about that. As long as the signature fits, we're like, that's plus, even if it breaks all the rules. That's just like, that's what we can do. There is like one, sort of like a get out of jail thing I use sometimes, which is that, I mean, these interfaces are in the BCL. And so will be widely distributed. You could write a Roslin analyzer that finds implementations of the interfaces and tells people that does not look right. If you're smart enough, you can grovel the code to as much detail as you like with the Roslin analyzer. We did not do that. I'm not sure we even thought about it. And I think it probably will be hard for some of the operators to say, this looks like a good implementation or this looks like a bad one. I think testing is probably better for that. Hey, but you could write your testing code generically. Actually, you could, write a test suite for math implementations that's completely generic. And then when somebody comes with a new concrete type that implements it, you just run it all and say, hey, sorry, but your identity was not an identity. Yeah, you screwed up. So actually, that would be possible as well. So there are several possible answers to it, but the honest answer is we have not done anything in that direction. Okay. I want to say one more thing about the language feature. I've been focusing a lot on math because that was really the driving scenario. That was the thing that made us do the hard work, and it is hard work to put a new abstraction mechanism into the runtime. That was the one where we felt it was worth it. But that said, the language feature itself has nothing to do with math. It just has to do with abstract static members and interfaces. And there are actually many design patterns that you can imagine doing more simply using this feature. One of them is, actually, let's go to iNumber. One of them is factories. So actually, one of these interfaces up here is a factory. I'm just going to go through the alphabet here quickly. Actually, not so quickly. Grab it and run. There we go. Parsable. There we are. iParsable. Let's go ahead and have a look at that one for a bit. And it's a little complex because it has two methods, and it takes an iFormat provider. But really, what it's doing is it's prescribing a static method that will take a string and create one of these guys, one of the T-self type, right? So it is a factory. If your type has this, implements this interface, then it is able to produce an instance of itself from a string, right? So now we can abstract over a factory. That means this could not have been done with an instance method because the whole point is you don't have an instance yet, you want to make one. And now you can have abstract static factories. You can take, remember all those, so people who've been going down the rabbit hole with factories, they have these parallel hierarchies of factory objects to create the hierarchies of actual objects, and it's like a mess. People do it a lot in Java. They don't do it so much in C# for some reason. But you see it, and you understand why people do it. You don't have to do that anymore now, because you can just have an abstract factory on the root, a root interface, and then everything will need to implement that, and that means you can create them abstractly. You can abstract over the fact that they have a factory. So you both have abstract factory and static factory in the same Go, static abstract factory. I think that's very cool. And we already are finding places where this pattern or other of the original design patterns can sort of be improved upon even in our own code. We have an example where we are using this for the strategy pattern already in some implementation detail. And so I think it opens up a new world that we haven't even really explored very much of ways that you can abstract that can reduce complexity of your code. Where you really want that unified abstraction of things, but they don't naturally show up as instance members, so you can't do it. Now you can. Okay? So that's I talked about it for a long time, but it is the biggest feature, and this is about how much time I expected to spend on it, because that is like the one that is, okay, since generics, this is the first time we added a new abstraction mechanism to the runtime. So okay, this is big, and it was a bit hard. So I want to spend some time on it to sort of justify, it's really important to. So with that, let's leave those behind, go and take a look at our numeric algorithm here, and then look at a different aspect of it. It's very imperative. It's old style, have an accumulator, zoom around in a loop, add the stuff, and then return it. Super imperative. We could try to do it more functionally. This is kind of like also a capstone on the previous talk then. It's like, where did we go with patterns? So one way we could also implement this would be via pattern matching, using the new list patterns that are in C#, in C# 11. So I'm actually going to just do it as I'm going to be brave, and I'm going to start out as an expression-bodied function here. It's going to be no statements will be used in this. It's completely organic. So let's take the values. That's what we have, and let's switch on them. A switch expression. Boom, and put a semicolon. And this is our implementation. And now, what we're going to do is we're going to take this list-like thing, like list patterns work on anything that has sort of the right surface area. And we can talk about what that is if you're interested in drilling in. But and then we're going to just look at the structure of the list using essentially list destructuring with list patterns. So the first case, the sort of base case is, hey, there weren't any values. Okay. Well, then the result is probably, it's probably not multiplicative identity. Actually, it's probably 0, or additive identity would probably do the same thing. So that's one case in the pattern. That's an empty list pattern. Or a non-empty list pattern, it could be, so now we're putting patterns inside for each element in the list. So I could say var t here for the first t, and I could put more. And if we want to start simple, we can just say, okay, let's deal with the case where there's one element in the list. So this will match only a single element array. In that case, you would just return t. That's a sum of t. Yeah. Okay, so far so good. And we could keep adding 2, 3, 4, but we're never going to get all the way. You're not going to like the feature very much if that's how you do things. So we're going to have to. We're going to have to go all the way into functional land and go recursive here. That's the only. And that means we're going to have to be able to grab like a rest, get the rest of the list. So I can pattern match on the first element maybe, and then I can have the rest just ... if I don't care about it, or ... var rest or t's, and that will then give me this gives me a t, but this gives me an array of t. It gives me back the same kind of thing that I came in with. So here be dragons from a performance standpoint, because it's going to give us a new array that's almost as big as the previous one. But we can fix that in a little bit. But so this one, and actually it doesn't have to be the last. You can have things after. You could have t2 here, or var t2. And by the way, these things can be other patterns as well. I'm just using var patterns to just extract the values without doing any pattern matching on them. So this is totally fine. It'll just grab whatever is between the elements in front and the elements in back. So you can only have one ... section in there, but you get to decide where. I'm not going to have something after. I just wanted to mention that. It's not restricted like that. And if we have that, then what we should be doing is we should be adding the t to the add all of the t's, and call recursively. And now we get like a lot of array allocation and copying going on. And so, you know, there'll be dragons. The reason why is that the way that this actually, the dot dot thing here works, like you can imagine, what is it actually doing to those list-like things when it is getting the values? You know, here, obviously, it's indexing, right? This is index 0. If I had one out here, it would be index hat 1, or hat 0, you know, if you have looked at the hat syntax for indices. So that's, you know, that's just indexing. And to get these, it is using the ability of that type to slice. So if it's sliceable, and we already have defined that in a previous version of the language, like you can have an indexer that is, you know, x dot dot y, and then it will slice those elements out, or throw if they weren't, if it was out of range. So we already have a notion of sliceability in the language. You may or may not have seen, but just trust me on that. And each type gets to define its own, what does it mean to slice me? And the sort of design principle for slice is that it will return the same kind of thing that came in, that you're calling it on. So if we want to do this more efficiently, we should have a type that is cheaper to slice. That's not array. And we have, this is not used very much in top-level code, but for performance reasons, we have a type called span of t. We also have a read-only span of t if you don't want access, which is really like a view on a segment of memory. For instance, a part of an array. And slicing for spans is super simple because it's really just a start and a length. So you just, you know, we move the start and reduce the length to create the next one. And they're value types, so we don't even allocate that little structure. So and the nice thing about I don't know. Oh, this is because I'm in a preview. I've run into this before. Don't worry about it. It'll still compile, right? Let's just check. No. What is my problem? It can't infer. You know, maybe because, I don't know. Never mind. We'll just pass it in. Double. And sorry about that. It's probably simple, but I'm on stage, so I can't figure it out. The nice thing about span is that arrays have a simple conversion to them, a simple implicit conversion from an array to a span that covers the whole array. So that would be a way to make it efficient. So the way that in a functional language this would typically be very efficient is that they typically use linked lists. And so if you're careful to slice off from the front, and oftentimes, you know, list patterns would only allow you to slice off from the front, then there's already like a list, you know, it's already a linked list of the rest that they can reuse. But here you get more expressiveness in terms of where you slice, but you also have to be more careful in terms of performance. Okay? And of course, patterns eagerly check that you cover all the cases and that you don't do stuff that can't be reached. So until we had that one, there was a warning on switch that would tell you like you weren't covering lists longer than one. If I took this one, which covers all lists, including the one with one elements, and I move it up, then we get an error on this one saying, hey, the one element case has already been fully covered, so you can't match it again here. So this is standard functionality of patterns already, but it also just to show that it works well for list patterns as well. So we can actually just delete that one because it's handled very nicely here. So that's list patterns. There's a question or two? There? Mm-hmm.
Why wouldn't it be possible to specify, instead of var in TS, have either array segment or span of T there, and then let the compiler take an as span behind the scenes and work with that? So allow us to change the type and then infer it.
It's possible we could do something like that. Yeah, I would kind of have to see it worked out a little bit to see if that would be possible. Again, an option is to have tool support for telling you, hey, it looks like you're doing a lot of slicing on arrays. Maybe you want to fix the code like this and have it be like an IDE gesture, a warning or a suggestion. But that's definitely, yeah. Typically when there are dragons like that, it's good to have some way for either the compiler or the tooling to help you avoid the pitfalls. One more, we'll take one more. Why should you prefer to? In this case, I mean, this case, it's maybe overkill. Pattern matching just generally tends to lead to more readable code. Also, as you saw, it gives you more checking that your logic is. So, compared to what you had before, which is very imperative, it's hard to like tell, am I off by one? Am I doing all the right things? And pattern matching, when it gave you it gives you the completeness and subsumption checking there. It's just keeping you more. The compiler's helping you more with correctness. Also, this combines with all the other kinds of patterns, like all the recursive kinds of patterns where you can have patterns within patterns. And so it's kind of a place where if I'm using patterns to destructure something, a structure, and I get to a collection kind of thing, and I want to do collection like destructuring on it, I kind of run out of steam now, and I have to grab it and take it outside of the pattern matching context that I'm already in, and this lets you stay in pattern matching mode when you get to those situations. So those are some of the arguments. We'll take one more.
This will give you stack overflow at some point, right? If you do it like this.
Yes. The point is this will give you stack overflow at some point, and that is also true. Like I'm not essentially I'm not really here to advocate recursive algorithms. It was just like a small example that is familiar to functional people. But yeah, we are not able to do tail call optimization on things like this and promise that and make sure that the stack doesn't overflow. This wouldn't even necessarily be a tail call. This isn't even a tail call. And so you're like, and if there are exception handling, so we don't do that kind of, we're not that functional. And so you have deep recursion, you have deep stacks. That's the C# way. And if you have a domain where you might go very deep, you'll run out of stack. Now, oftentimes the places where recursion is good in C#, they're typically where you're recursing over some data structure, and then you have much more of a handle on how big it can get. Your data structure is probably not going to be all that much bigger than the stack, or it'll be more on the same order of magnitude. So there it makes more sense. Okay, so that's list patterns for you. Let's switch gears and go talk about persons again. I can't remember the last time I talked about new C# features and didn't have a person class. So it's kind of traditional. This time, though, I'm going to change it into a person struct. Just shake it up. There you go, person struct. You notice that that's fine. And for people who have worked with, maybe people don't work with structs, but if you work with structs and you look at this for a bit, you'll be like, why is it fine actually? That would be an error here in C# 10. The reason is that since the dawn of time, for structs, we have required constructors to initialize everything. Like if you have a constructor in a struct, it must initialize all the fields. And we meticulously check in the compiler and say, yep, you didn't initialize that one. Not in a way that I can see anyway, so error. And we're like, well, why are we doing that again? Maybe we're trying to not bulk zero initialize things for efficiency maybe. But couldn't the compiler, if it's figured out that you're not initializing it, couldn't it just go and zero out that one? Instead of telling us that we're dumb, couldn't it just do it for us? I'm like, that must be a deep reason. We went and talked to Anders Heilsberg, who's the oldest C# designer around. And what is the deep reason, Anders? What was the wisdom behind this? And he's like, I don't know. I don't know. It doesn't seem important. Okay, we'll do it. We'll fix it. And this is important now because we've done many more things recently to make structs more versatile. We made them able, in C#10, they're able to be records. They're able to have primary constructors and all kinds of things where we keep running up against this limitation. You keep doing something and you get this error and you have to do stupid stuff. We let you have field initializers in structs now. And again, once you have a field initializer, but you don't have it on everything, then you're like, well, then you get slapped for all the ones that you're not initialized. Let's just fix this instead of chasing all these weird corners of the language. And we do have actually, if for some reason you really like pain, you like this error. I mean, some people are like, I want to make sure the compiler doesn't do anything for me because it wastes valuable time or something, and I know what I'm doing. Famous last words. We actually do produce a diagnostic in the Roslyn compilation tree, and it has a diagnostic number like CS some number that we produce whenever you do not initialize everything manually. Then we do initialize it for you. We still produce a diagnostic. It's just not a warning or error. Like it's just an info, but you can go make it an error if you want to. So because it exists, because the compiler puts it in, you can raise that level to warning or error, and you can get back your pain. Because we weren't entirely sure some people, there might be reasons we hadn't thought about. Let me just put it. So we're back to classes though. We did a few more things around classes. Like for the last couple of years, we've tried to be serious about immutability and value semantics for classes as well, where you can still have class hierarchies, and the sort of class level expressiveness, still have them be reference types so they can be recursive, yet have value semantics as opposed to object semantics. And that's again in sort of the functional vein of, I actually want to work with immutable data. And the language has been fighting you in every step of the way. And we are trying to remove some of that pain of when you're trying to go in those directions in various ways over the years. One is records, which we've done nothing new with records since C#11, so I'm not going to go there. But I mean, the pain of having to have constructors is an obvious one, right? And an alternative to having construct. Let me just go and comment out my code here, so that I can use top-level statements over here instead. If I want to say var mads equals new mads, because it's immutable, in the past I would have had to use a constructor. I couldn't use an object initializer, but the constructors are just really super painful. I have to have two because the middle name is optional, but optional parameters have to go on the end. But I don't want the middle name to be at the end and the last name to be in the middle. I mean, so I kind of I have to have this overload. And now I want to create class student or employee or whatever, and it's a person. I haven't even done anything yet, and I'm already in debt, right? Oh yeah, you have those constructors. You got to deal with that. So it's like constructors are painful in many ways if you have hierarchies or several overloads. And sometimes you just want things to be easier, and object initializers are a way for that to be easier, to just live without constructors. But they lack certain things. And in, what was it, C#9, so one of the things they lack is, or they used to lack, was that if I have an immutable data structure, they rely on mutation. So if I say first name, new mads. I'm not a class yet. I'm 25 years at Microsoft, they turn you into a class, but I'm not there yet. First name equals mads. Let's just stick with that. It says you can't because sorry, it's actually getter only. And then we said let's add this kind of setter that only works in object initializers. We call it an initter, and so you might have seen all this before, because that's not new, but it's just part of this story that I want to get us to there. And that kind of took care of the initializing immutable things with object initializers. The next thing, though, is that I don't want people to not give a first name and a last name in this object model, at least. I know that it's not a good object model for names. I should, remember to say that. But this one can, it's okay if they don't initialize middle name, but I want them to initialize first and last name. I want to force them to do so. I could do that with a constructor. I was doing that before. There was no constructor that didn't. So there, So that's one place where object initializers still kind of have a gap of expressiveness. And that kind of interferes in an annoying way with nullable reference types as well. Because you're seeing these warnings here on first name and last name. And what those warnings are saying is, you're not initializing this non-nullable property, which means it might be null when the object is initialized. Yeah, but I want people to do it themselves. Yeah, but you can't be sure they will. So I'm going to give you a warning. Now, what we really need is a way to ensure that they will. Like we're going to give you a hammer to say, this is required. This is required. You can't not. You can't not do it. And now the warning goes away because it's like, yeah, you're making them do it. I'm good. I'm good now that this will not be null. Because if they go and put null in, they will get the warning and it'll be their problem. So this fixes the nullable problem, and it's also just fixes the general problem of I couldn't force it. That difference in expressiveness. So now I made last name required, but I didn't do it. I get an error. Everything's good. It's just hunky-dory. You can't do this in the previews yet, I think, because it just came out in the internal preview that I'm using. But soon. Or maybe you can. Was there somebody here? It is out in the public preview?
If you create the required attribute,
yes.
required member attribute manually, and you put in the namespace, it works.
The attribute that we use under the hood to put the required on things isn't in there. So, but you can cheat and go and. So I've done that. There's like a file in here that has a declaration of that attribute, and that's why it works here. So this is how it's going to work. And of course, then, when I actually get a last name, it's going to be happy. And these are inherited, obviously, so the cumulative down through inheritance hierarchies. If you have a constructor that is like, I don't want it to do it here. It's a good example is a copy constructor. I have an immutable data type. I want to actually create the next record for MADS. And I want everything to be the same except what someone optionally chooses to put in an object initializer because they explicitly want to change it. That constructor shouldn't force everybody to put everything, right? It shouldn't force them to call me MADS again. The constructor just did that. So we talked for a long while about what should be the granularity of opt-out mechanisms for that. And in the end, we just ended on an attribute which is also not there, and I can't show you because I can't remember what it is, and I forgot to declare it. But there's an attribute that you can put on a constructor to say this one is exempt from requiredness completely. So it's all or nothing. You get all the required or none of the required, and none of the required is no worse than today. It's just that's the fallback if you know what you're doing. So we figured that was the right balance, but if we need more granularity in the future, hey, there's a next version coming next year, and we can always make it better. Now we can granularly improve features. We can take the cautious approach at first, and then when we find out, hey, we may need a little more here, it's actually worth it, many customers reporting, then we just do it. Okay? So that was required. There's one more one question.
First of all, thank you so much.
You're welcome.
Generate a zero-argument constructor for like JSON serial things for this class?
This does not change what constructors get generated. Now, and it doesn't. The required restriction isn't maintained through reflection. We talked about like how can we make that actually a strong requirement that even works through reflection, like when you have a serializer or something using reflection to create the object. And we're like, actually, read-only isn't even enforced during, through reflection. So why should this be? It's like, yeah, all bets are off when you go that direction. For constructors that people generate for specific purposes, like that, they could slap that attribute on if they want to not require object initializers to be used. Let's take, there are a couple of questions now, and I do have 2 more features to go. Can we take them after? All right, I'm going to just stay here while everybody else goes and grabs all the good stuff at lunch, or we can walk up together or something. But yeah, I want to get to the last 2 features. Apologies. One that I want to show quickly is, it turned out, auto properties turned out to be really awesome. Because very often you really just want a backing field and you want to read and write from the backing field and done. But the moment you want to do just a tiny little bit thing more, you fall completely off the cliff and you have to declare your own backing field and you have to implement both of your accessors yourself. Like there's no middle ground. And we are introducing the middle ground. And we do that in form of field access. Like you can access the backing field from an auto property using the innovatively named keyword field. This is not in my prototype yet, so there's going to be squiggles, but this is what it's going to look like. So what the set or init accessor is generated to do is just to take the, the backing field, which we can now name field, and escape out of all those suggestions for completion, equals value, right? That's just what it does. But what if I wanted to just, trim it? Yeah, I don't want white space accidentally in my first name. Now, I would fall off the cliff before, but instead I can implement the initter manually just by referencing the backing field with the keyword field. I don't have to use the getter, or to implement the getter myself. I don't have to declare the backing field. So it's more of like an incremental step instead of falling all the way off of the cliff. And we do the right things. If you have questions about, does it do the right things? Yes, it does the right things. So that's coming. I don't know what preview, but everything else I've shown so far, you can actually go try just using the VS previews, but not this one yet. Here's another one. Actually, it's not here because I'm going to show it in. I'm going to show this in my favorite browser. Using SharpLab, which if you don't know SharpLab, it's awesome. It's a community-run website that offers up all the latest branches of the C# compiler in an interactive way that you can play with it. And I'm just using main because we did merge this feature, but in here is a lovely menu of like all the stuff we ever did. Some of it is broken, but that's the risk you have. But it means even if a feature is not out, you can still use it here. And I think possibly the field access thing that I showed before, you might actually be able to go in and try it here, but I haven't tried recently. What I want to talk about is raw string literals. So there's a bunch of times where you just want to have some code in a string in your code, and it can be C# code. Oftentimes it's like, were you also distracted? It's kind of cute. It's cute. Do you have a cat in your pocket, or is it just a phone? No, yeah. Okay, no, it's very gentle. I love it. Code can just be XML or JSON or whatever. The main problem about it is it'll have a lot of characters in it. What I mean by code is something that has characters in it that's going to confuse string literals, like backslashes, like that look like escapes, but you really just want them. And the pain of converting things so that they will end up being the right thing after the literal has been just like everybody knows this. And even like verbatim strings don't fully solve this. So we wanted to create yet another form of string literal in C# that has no escapes, period. There are no escapes. You cannot escape. And the way we do that is that we make you put at least 3 double quotes on either end. And now you can see the backslashes, they show up correctly. They're no longer escapes. So actually, I want to remove them because they don't actually belong in the content. So now what's in there is just the content that I want. No escapes. That's nice. Well, okay, somebody's like, yeah. What if I have 3 quotes in my content? Oh, you got me. Oh, what am I going to do? I'm going to put 4. What if I have 16 quotes? I'm going to put 17. You can always win. It might not look nice by the time you win, but the only reason you would have 16 double quotes in a sequence in content is because you want to capture a demo of this feature in you know, as a string. You know, actually, I have this as a constant string in code somewhere, and it, you know, it has to use 4 quotes because it has the triple quotes in there. Usually 3 is enough, but you have an escape that's not an escape, if you know what I mean. These can be multi-line, and if they're multi-line, you have to like have a new line both before and after the content. And that new line is not part of the content. That is part of the delimiters. So the content here is still like, it has no new lines in it. But it's now multi-line. It's one multi-line, but we can start, you know, breaking it over lines. And, well, let's do one there as well. Hello. There we go. Well, you might notice that, well, you just told me that we just get the raw content, but I'm noticing that some white space is going missing here. Yeah, what's with that? Are you cheating here? What's going on? So, what is it that happens? So let me. Yeah, I mean, I would actually probably want to indent this and a little bit. And what you see is that indentation gets picked up. So what is going on here? Like what white spaces are in and what white spaces are out? What's the deal here? The reason for it is obvious. It's like it's really annoying when you're quoting multi-line things and they flush completely to your left margin, right? And all your code flow is up there, and then something bad, it takes all the attention, and it's even red. You know, then it's a string later on, it takes all the attention by being out. And it's like just looks stupid. And so it's really nice if you can avoid that by just having the white space clipped off. But what if I don't want it clipped off? Well, we got something for you as well.
More quotes.
What's that?
More quotes.
More quotes. No, no, we're done with that. But the way we do it is that the number of white spaces before the end quotes is what determines how much gets cut off. So if I move this to the left, you see that I get one white space in there, and there, and there. And if I want the full thing, I just flush the end quotes all the way to the left, and I get all the white space. Does it work the other way? Interesting. Let's try. That's a good thing about interactive stuff here. Let's go one over. Ah, no, sorry, you can't do that. No, it's like, what are you doing?
Mix spaces and tabs.
Exercise for the reader. Good one. So now that quoting is great, having like actual good literal, raw literals is great. But what if you do want to interpolate just a little bit? We still want to stick some content in there. Like, can I interpolate these? You know, because no escapes, right? So if I put something in here that's like 3 + 4, that's just content. It's, you know, just content. What if I want to interpolate? Well, I can do that. Just put a $, and now it's interpolated. Now the single brackets delimit a hole, and the expression inside gets evaluated and toString back in. Awesome. Well, what if I want interpolation and curlies? $2. Have you been at this talk before?
I'm sensing a pattern.
Now they're content again, because it takes the $, number of $, is the number of curlies it takes before it's an interpolation. And now it's a little ridiculous, but it is actually like, it's super useful. Now we can do this. Oh, I have a problem like getting it to click in the right place here. Now we can do this, and it's interpolated. But if you only have single ones, you know, they're content. Or if you want your single ones around the interpolation, that's fine too. And then you get, you know, single quotes around there. If you want double quotes around there, you know what to do. Add a $, use 3 for the interpolation hole, and then you can put your 2, and they're not an interpolation hole anymore. So you can still win. And I mean, I'm making it a little hilarious here, and you're like, you can see how this can get a little ridiculous. But the important thing is, we are not forcing you to change things when you want to quote them. We're just maybe making you put a lot of quotes around them, So you don't have to go and find those escapes, and you don't have to read the fine print of your output. And we're still allowing interpolation even when you want curlies. Like we are not falling for the temptation to put escapes back in even when it's interpolation. So hopefully this is one for the ages. This is the one. This is the one that is going to let you quote all the things forevermore. That's the plan anyway. And that was the last feature I was going to show today, which is lucky because we're actually we're at the end of time. I can take one question. Yep. What? Sorry? What if you want a string to start with a double quote? You use the multi-line version of it, even if it's just a single line, because then the quotes on the top line here are part of the delimiter, and the quotes on the next line are the first part of the content. That is why we don't use the new line as part of the content. You know, the content starts here and ends here. So you can do tricks like that. Same at the end, right? There's always a way. Or at least I haven't found a hole yet. And with that, I want to say thanks. It was great questions, and I'm still around. There's going to be lunch. I'll be around there somewhere. If you have more questions, more ideas, you know, grab me now. Shoot me an email later. I'm just mads.torgersen@microsoft.com. I don't mind sharing that, just with my 100 closest friends. 100, I don't know, some number. And I hope you enjoy C#11. Thank you.